I am going to explain about phases of compiler design. First, let me discuss about what is compiler. So a compiler is also a program which it translates a source code which is given by the user, converts it into the low-level language which can be understandable by the machine, and it can able to identify the errors whether a user has been written the program completely following the rules of the programming language or not. So for that, today I'm going to explain about the phases of the compiler design. So compiler, while it is going to be translating input source code into the machine level language, it is gone through different phases. So first, compiler operates in various phases. So each phase has its own responsibility to execute while it is going to be translating from source code to the machine level language. So each phase transforms the source program from one representation to the another. Each phase takes inputs from its previous stage, and it will be acting as the output of each phase will be acting as an input towards the next phase. So mainly there are 6 phases are involved in the compiler design. So each phase is going to be converting the high-level language code into the machine code. So every time it goes through a source code or a statement goes through with each phase, it is going to be having the different transformation. So for example, here we are telling that a compiler has been designed by using the 6 different phases. So the first lexical analysis, second one is the syntax analysis, third one is the semantic analysis, fourth one is the intermediate code generator, fifth one is the code optimizer, and sixth one is the code generator. So the source code has to go through all these different 6 phases to convert from the high level language into the machine level language. So for example, here we said each stage output will act as the input towards the next stage. So now the main input of the compiler of first phase, that is the lexical analysis, the input for this lexical analysis will be the source code or a source program which is written by the human being or which is written by the user by using a high level language. So this high level language may be any language, maybe C, data structures, Python, Java, .NET, whatever the programming language the user can use to write. And that compatible compiler will use all these 6 phases to convert this high level language code into the machine level language throughout the compilation process. So let's discuss in detail about each and every phase of the compiler. So this is the flow of different phases. So we can say this diagram shows you how the each and every phase of the compiler will flow from the high level language by transmitting it into the machine code. So here you can able to see the input. So this will become the input. So here input is the high level language, nothing but any source code written by the human being. So from this is the input to the first phase. This is the first phase of the compiler. That is the lexical analyzer. So this lexical analyzer are having few responsibilities. So here it does all these responsibilities, or it completes its functionalities in this phase. After completion of lexical analyzer phase functionality, some output will be there. That output will become the input towards the second phase, that is the syntax analyzer. So the same way, each phase output will become the input towards the next phase until a source program has to go through all these 6 phases compulsory. And finally, whatever we got is the output of the compiler, that is the compilation. So the compilation of a program will complete whenever the input can be completely converted into the machine code. So in between all these phases, any error has been identified in any phase, that will be reported towards the error handler. And the symbol table acts an important role here. The symbol table is going to be maintaining how the conversion has been taken, or how the transformation has been done from the high level language towards the machine level language from each and every phase. So each and every phase output will be registered in the symbol table, and if any phase has been identified any error, that error will be reported towards the error handler. By that, a user can correct it, and he or she can again execute or compile the program. So all these phases converts the source code by dividing into the tokens. The first transformation starts from dividing the source code by identifying the tokens present in the source code. By using these tokens, it can able to construct a parse tree. By constructing a parse tree, next step is it is going to be optimizing the source code by removing all unnecessary statements, and all this can be done by using the different phases of the compiler. So let's start with the discussion in detail about the each and every phase of the compiler. So here we can divide these 6 phases into the front end and the back end dependencies or independent of each every phase. So here you can able to look first 4 phases, that is the first 4 phases: lexical analyzer, syntax analysis, semantic analysis, and intermediate code generation. All these 4 can be comes under the front end, that is the machine independent. So these 4 phases can do its functionality without any machine dependency. It can do individually without having any support of the environment of the machine. And remaining last 2 phases, that is the code optimization and target code generation. These 2 phases can comes under the backend, that is the machine dependent. So like this, the different phases of the compiler has been divided into the 2 parts, that is the front end and the back end, which is machine independent and the machine dependent. Let's discuss about in detail about each and every phase. So first, coming to the phase 1, that is the lexical analysis. The main responsibility of the lexical analysis phase, that is the first phase of the compiler, is it scans the complete source code. The main input for the lexical analysis phase is the source code which is written by the user. The first functionality or the first responsibility of the lexical analysis is first it scans entire source code which has been received as the input, and this process can be done from the left to right by taking character by character, and these characters are going to be grouped into in the form of a tokens. So we can call a group of characters can be called as the tokens. So here, whenever a character by character has been grouped, we can call it as a stream. Right. So these character stream from the source program, whatever lexical analysis has grouped, this sequence of identifying the meaningful character stream, we can call it as the tokens, and it makes the corresponding tickets into the symbol table by passes these tokens into the next phase. So the first input to the lexical analysis is the source code. By scanning the source code, by reading character by character, it forms a stream of characters, and these stream of characters can be meaningfully generated as the tokens. So these tokens are first stored into the symbol table, as well as these tokens, the number of tokens which has been identified by the lexical analysis phase will be given towards the input towards the next phase. So the output of the lexical analysis are the sequence of tokens by scanning the entire source program. So what are the responsibilities of the lexical analysis? The first one is identifying the lexical units in the source code. So lexical units is nothing but the sequence of characters forming a meaningful sentence or meaningful words, which we can call it as the tokens, that can be referred as the lexical units in the source code. And classifying these lexical units into it's a group, nothing but we can have constants, variables, or keywords, which are or we can call it as keywords or the reserved words in the programming language. So these can be identified and these can be classified into its classification by identifying which token will be classified into the which type. Either it is a constant, or it is a reserved word, or it is a data type, or it is a constant, variable. So these can be considered. And remember one thing here, the comments which has been written by the user in the source code will be ignored in this phase. It cannot comes into the compilation process. The comments whatever written throughout the program will not be compiled. This can be ignored in the initial state, that is the lexical analysis phase only. So by identifying the tokens which are not part of the language, that can be reported as the comments in the lexical analysis phase. So here I have given a simple example how to how a lexical analysis phase will identify the tokens, and it can be grouped into which classification. So let's consider one simple statement, some x is equal to y plus 10. So by scanning this statement, the lexical analysis now by scanning this statement, it is going to be identifying how many number of tokens are there in the statement. So first x is there, so x will be considered as one token equal to y plus and 10. All these can be considered as a tokens. So the explanation for these tokens will also be given by the lexical analysis. So the x can be considered as the identifier, equal to is the assignment operator, and y is on another identifier, plus is the addition operator, and 10 is a constant or a number. So it is going to be identifying 10 as a number or a constant. So like this, for entire source code, the tokens are going to be identified by the lexical analyzer. That is the first phase. Now, so this is the input by user to compiler. So now the lexical analyzer input will become this one, and the responsibility is identifying the tokens. So these are the list of tokens identified in the lexical analysis phase. Now this sequence of tokens will become the input towards the second phase of the compiler. So this will become the input to next phase, but actually it is the output of lexical analysis phase. So this is the output for lexical analysis phase, and also it will become the input towards the next phase, that is the syntax analyzer. So next, coming to the syntax analyzer or syntax analysis phase, or the second phase of the compiler design. So the syntax analysis is all about discovering structure in code, whether the written program by the user followed all rules of the programming language or not. So it determines whether or not a text follows the expected format or not, whether the source program written by the user follows a format given by the programming language or not. It is going to be concentrating on the mainly about the format. So mainly the aim of this phase is to make sure the source code was written by the programmer is correct or not. So the syntax analysis is based on the rules based on the specific programming language by constructing the parse tree with the help of tokens, whatever the tokens received from the lexical analysis phase. So by using these number of tokens, it is going to be constructing a parse tree. So here we can say the tokens are input to the syntax analysis phase. So by this tokens, first it is going to be checking whether the expression the given by identifying the tokens are syntactically correct or not. It is checking for the syntax, whether the syntax written by these tokens are properly given or not. Next, if any errors it is identified, then the errors will be reported towards the error handler, or else it is going to be, if everything has received from the tokens received from the lexical analysis phase is correct, syntactically correct, then it starts constructing the parts tree by following the hierarchical structure. So let's see an example. So here it is an example, A plus B into C. So any identifiers or numbers is an expression. So now here, if x is an identifier and y plus 10 is an expression, then x is equal to y plus 10 is a statement. So just I am going to be variating what is identifier, what is expression, and what is statement. So if we have only one identifier, x, y, z, all this will become the identifiers. So if we are writing any computations by using some operators between these three identifiers, then it will become the expressions, right? So by writing some expression, we are getting some calculation, we are assigning some value to another identifier, then we can call it as a statement. So now consider this simple statement to construct a parts tree. So here by constructing the parts tree, we should know which one should be taken as the interior node, which should be taken as the leaf node, and a way to stop the parsing actually. So for that we need what is interior node, what is the leaf node. So here you can able to identify in this statement the record with an operator field and two files for children. The root node should definitely consist of two children, that is the left and right, and the middle one should be an operator. Then that can be considered it as the root node. Coming to the leaf nodes, so records with two or more fields, one for token and other information about the token, that can be considered it as the leaf nodes. So ensure that the components of the program fit together meaningfully. So whenever in a syntax analysis phase, if it construct a parts tree, finally it should have some meaningful statement, or finally it should be can be a one particular statement which can be executable. So it gathers the information and checks for the compatibility, whether it can be executed or not, or by using this parts tree we can able to check whether this can be a computed possibility, computation can be possible or not. So like this, every statement or a group of tokens which are received from the lexical analyzer, the parse tree is going to be constructing. So for this expression we can able to see, so this into is consider it as the root node. By this taking it can have the two leaf nodes, so that the into right side we have the C, so that the right child we have taken C, and the left child again we have two identifiers. In between the two identifiers one more operator we have, so that we have considered place here, and for place A will become the left child and B will become the right child, so that it is going to be finding out whether the statement is correct or not. Next, coming to the third phase of the compiler, that is the semantic analysis. So now this parts tree will become the output to third phase of compiler. So now this is the input towards the next phase, that is the semantic analysis. So semantic analysis checks the semantic consistency of the code. That is nothing but whatever the parse tree has been constructed by the syntax analyzer, whether that is semantically consistent or not, a proper meaningful parse tree has been constructed by the syntax analyzer or not, or if any type conversions are needed, that can be done automatically by the semantic analysis phase. That is the actual responsibility of the semantic analyzer. So here it also checks whether the code is conveying an appropriate meaning or not. Also mainly the concentration of the semantic analysis is whether it is having a proper meaning or not. So the semantic analyzer will check for type mismatches, incompatibility operations, or a function called with improper arguments, or any undeclared variables are there. So this type of checkings are done in the third phase of the compiler. So let me see the main functionalities or the main responsibilities of the semantic analysis. So it helps to store a type information gathered and save it in the symbol table, so which allows to perform the type checking. It is going to be perform the type checking also. So if any type mismatches, it identified in checking, if it identified any type mismatches, so then if no exact type correction rules will satisfy the desired operation, a semantic error is shown. Or if it is compatible, and if a data type can be able to change it into the another data type, if it is a compatible, then automatically in the compilation time itself the semantic analyzer will convert the type of variable from one data type to the another data type automatically. If it is not correct, beyond the rules, or if it is incompatible, then it will be reported as an error towards the user, and now the error has to check whether which data type it has to be declared. And it also collects type information and checks for type compatibility, and the source language permits the operations or not. It also checks whether the operands whatever used for the construction of the parse tree or possibility of having the meaning or not. So here I have given one example. Suppose we have x as a variable which is of float type, so that float type is going to be accepting the decimal, so 20.2. So now we are going to be having one more variable y, which is having some expression or we can call it as a statement. So y is equal to x into 30. So now x is having the 20.2, which is the decimal, and 30 does not have the decimal. So that here the semantic analyzer will typecast the integer 30 to float by using that 30.0. So converting the 30 into the floating point before multiplication. Before doing the multiplication itself, the semantic analyzer what it is going to be doing, this 30 is going to be converted into the 30.0. Why? Because the y is the float type, so the answer which is doing this calculation should also be the decimal points. So this 30 will be converted into decimal points before doing the computation. So like this type compatibility is there, then automatically it is going to be converted. If the type conversion cannot be possible, then it can be reported as an error towards the user with the help of the error handler. So next, coming to the fourth phase, that is the intermediate code generation. So now whatever the parse tree has been given from the syntax analyzer to the semantic analyzer, it checks the meaning of each and every leaf node, root node, everything from the parse tree, and the same will be after checking if any conversions are needed, it done automatically conversions. Then now whatever the output generated by the semantic analyzer will become the input towards the intermediate code generation. That is the fourth phase of the compiler design. So once the semantic analysis phase is over, the compiler generates intermediate code for the target machine. Actually the transformation, the main transformation of high level language will be starts from here. Up to now, first three phases are going to be checking whether a statement has been written properly or not, by making or by following each and every phase responsibilities. Actual transformation of the source code from high level language will start from the fourth phase, that is the intermediate code generation. So here it generates the 3 address code. So it represents the program from abstract machine, and intermediate code is a between the high level language and the machine level language. So this intermediate code needs to be generated in such a manner that which makes it easy to translate into the target machine code. So now the intermediate code generation responsibility is to convert this high level language into the machine level language or the machine readable code. So the main functionality of the code generation is it should be generated from the semantic representation of the source program. So the conversion of high level language into machine level language can be done only with the help of the output which is generated by the semantic analysis phase only. So it holds the values computed during the process of translation. No values or no change should be done to the actual input, and helps you to translate the intermediate code into the target language. Allows you to maintain precedence ordering if the source language, and it holds the correct number of operations of the instructions. How many instructions has been written by the user, that many instructions should be executed finally. It should not change any meaning of the code. So this is the example how for a statement how the intermediate code will be generated. Actually it is going to be following the 3 address code to generate the intermediate code of a high level language. So here we have taken some expression, that is total is equal to count plus rate into 5. For this statement, how the intermediate code will be generated. So for intermediate code generator, it is using the 3 address code mainly. So 3 address code is nothing but using the temporary variables for the computations, and the one rule here we have to consider is no more than 2 variables should be taken at the RHS side. So LHS is equal to RHS. These RHS side you should follow the rule is no more than 2 operands can be considered. Either we can take 1 or we can take 2. So no more than 2 will not be taken at the RHS side. So that first for T1 as a temporary variable, so here we have the count plus rate into 5. So here we have the integer value, but whenever we are doing with the rate, definitely we are going to be getting the value of some decimals. So that first it is going to be converting this integer value into the float value, so that it is going to be assigning T1 equal to conversion, that is into 2 float of which value, the value is 5. So next considering T2, so already in T1 we have the 5, so the 5 will be multiplied with the rate. So in T2 we have the rate into T1, and now in T3 already rate into 5 we have in the T2, so that we have written count plus T2. Now this T3 is holding the result of count plus rate into 5, so that is assigned directly towards the total. So like this the 3 address code will be generated by the intermediate code generation, and this will become this is actually output of intermediate code generation, output of intermediate code generator, and input to next phase. So this is the input of the intermediate code generator phase, and as well as it will become the input towards the next phase, that is the code optimization. So the main usage of code optimization is to make to better the compilation time, to reduce the compilation time. If too many statements are there, then the compiler will take much time for the compilation. To reduce this compilation time, to make the better usage of the execution time, the code optimization phase is going to be reducing the reducing the statements. By reducing the statements, it should not change the actual source code written by the user. Just it is going to be checking whether there is any possibility of rewriting the code by using the less statements. So here it helps you to establish a trade-off between execution and compilation speed. It makes the much better of the speed of the compilation, and it improves the running time of the target program, generates streamlined code skills in the intermediate representation, and removing unreached code and getting rid of unused variables. It checks whether variables has been declared, used properly or not. If it is declared and but not used throughout the program, it is going to be deleting it, or it is going to be eliminating it from the compilation, not from the source code but only from the compilation. It is going to be removed, and removing statements which are not tottled from the loops. So all these responsibilities done by the code optimization. Let's give an example for this. Suppose we have a few statements to identify how these 4 lines of code, how these 4 lines of code has been optimized into the two statements, right? So we have a is equal to int to float, that is the 10 value. It is an integer value from the statement, but it has been converted into the float, and some b is equal to c into a, and d is equal to e plus b, and f is equal to d. So carefully look into these 4 statements. These 4 statements have some unreachable code, or so that if it is an unreachable code, then directly we can remove it by with the help of the code optimization phase. By this we can improve the efficiency and we can improve the speed of the compilation. So you can see, so we have a is holding the value of 10.0. Why? Because integer has been into float. So now a is equal to, we have the a is equal to 10.0. So and b is equal to c into a. So again we are storing a 10 into a, and we are doing multiplication with the c and storing in the b. Instead of it, directly we can write b is equal to c into 10.0 directly. No need of assigning this 10 again into a. So by this we are reducing one statement, and you can see here d is equal to e plus b and f is equal to d. So d is holding the value which is calculated after e plus b. Again d is holding into the f. So we can say we can directly write f is equal to e plus b. So we can remove d here. There is d is unnecessarily written twice. So like this we can reduce the statements to make the compilation efficient, and we can improve the speed of the compilation also. So like this, if any statements are there which are unreachable statements or unnecessarily written twice, or unreachable code, or variables declared but not used in the program, that type of variables or the statements can be identified and can be removed by using the code optimization. Next, coming to the last phase of the compiler, that is the code generation, where actually this converts into the machine level language. So the code generation is the last and final phase of the compiler. It generates the inputs from code optimization phase and produces the page code or object code as a result. So whatever the output of the code generation, we can call it as the object code. Actually it is the format of machine level language. So the objective of this phase is to allocate storage and generate relocatable machine code. It also allocates memory location for the variables. The instructions in the intermediate code are converted into machine instructions. This phase converts the optimized or intermediate code into the target language. So here you can see, up to now we have done transformation with the help of the high level language only. Now these high level language will be converted into the machine level language, or we can call it as a object code language. So here we have the one example, or we have taken one statement like a is equal to b plus 60. So this can be converted into the assembly language, or we can call it as the mnemonics. So here for these statements we have the statements which are written in the machine level language. So now a is there, so to store the a, one register is needed, so that we have written move a comma r1, right? So next we have the one constant value, and this it should be need some storage, so that we have taken 60 in the register R2, and then we are going to be adding it. So whatever we have in the R1 and R2, R1, R2 will be R1 and R2 is going to be doing the multiplication, and it is going to be stored in the R1. So like that it is going to be, these statements are written in the mnemonics format. So actually here we can write it as move A into R1. So whatever the value will be there, that will be stored in the A. Now we have the B plus 60, so that we can write it as move B comma R2, and we can write add R2, sorry, we can write R1 comma R2 comma 60.0. So nothing but whenever we are writing the three statements or three resistors or two resistors with one constant value, it means that the value 60 will be added with the R2. Whatever the R2 holds the value, that will be added, and the result will be stored in the R1. Or else we can write it directly as add move A comma R1. So now we can have move then add R1 comma R3 comma R2, so that R2 value will be added to R3, and the addition of between these two will be, and the result will be stored in the R1. So like this, the final programming language or the high level language has been converted into the machine level language. So from this language, now this language will be the, we can call it as a object code. So this object code can be furtherly converted into the zeros and ones, which can be easy to convert these statements comparing to the high level language, and this will be converted into the zeros and ones. Then the compilation will be completed. So let's see one example. Okay, let's see one example so that we can able to understand how each and every phase is going to be doing its functionality to convert the high level language program into the low level language. So now I have taken one example, x is equal to a plus b into 50. So the symbol table for the above examples are given in the below. The symbol table are clearly mentions the variables names and the variable types. So the now for this statement, the symbol table will be like this. So we have the three variables here, x, a and b, so that the symbol table is holding the variables which are declared in the program. So like that, a symbol table holds, it scans first source code completely, and it is going to be identifying how many variables and which type of it. So now we have taken x, a, b, and all three are the float types. This information will be stored in the symbol table. Alright, initially the symbols table will store the information. Next, coming to the first phase, lexical analyzer, for the same statement, that is a x is equal to a plus b into 50. This is the statement. For this statement, the first phase, this will be the input. This will be the input towards the lexical analyzer phase. So the lexical analyzer phase responsibility is identifying the tokens, right? So for this, it is going to be identifying the tokens. So that is x equal to a plus b into 50. And now for this, the lexemes are going to be identified. These are the tokens, and the description for the tokens can be called it as the lexemes. So Here x can be considered as an identifier, is equal to is an operator, a, b will also be identifier, plus into or operators, and 50 are the constants. So here for clarification I have given how the parse tree can be calculated. So whatever the identifiers are there, first identifier as the tokens will be given in the sequence. So the x will be considered it as the identifier 1, a will be the identifier 2, and b will be the identifier 3, and the values whatever we have considered here is the constant, and we can have whether it is a integer type or a decimal type, whatever it is we can consider here, and we have taken here assignment, binary addition and binary multiplication. So now the tokens has been identified, and these tokens will be given towards the input towards the next phase. So now this will become the output, which is an input towards the syntax analyzer. So the tokens are given as id comma 1, that is the identifier 1, identifier 2 plus identifier 3 into 50. So this is the output of the lexical analyzer and input towards the syntax analyzer. So now the syntax analyzer will construct a parse tree for this. So here it is considering it as a grammar, like a grammar first it is considered, then it can able to construct the parse tree easily. So now it has taken s is equal to id, so that is nothing but it has taken one production, and that e is equal to e plus t or t is equal to t into f, if is equal to id or a integer constant. So with the help of this grammar we are able to construct the parse tree with the help of the tokens given by the lexical analyzer. So first s has been taken, s is id equal to e. So here we have the x is equal to a plus b into c, a plus b into 50, right? So here x can be considered it as yes, and e can be considered it as a can be considered as e, and t can be considered, b can be considered it as t, and 50 will be considered as ef. So like that, for a given grammar we have to consider the tokens given by the lexical analyzer. By that we can construct. So here s equal to e can be considered e plus t or t, but to get this statement definitely we should have the addition operation. So instead of e it has been constructed as e plus t. So and e it has directly get some identifier, so that next e has been derived by t, and t is derived by f, and f is derived by the identifier. Like this a parse tree can be constructed from the considered sequence of tokens. These parse tree will become the output and input towards the semantic analyzer. So in this semantic analyzer it checks any type conversions are necessary and the constructed parse tree is meaningful or not. So here you can able to see f is going to deriving 50, and here typecasting has done automatically by the semantic analyzer. So the integer will be converted into the float for the convenient and compatibility. If it is a compatible, then it converts. If it is not compatible, then it reports an error. Next, that after checking the meaning of the constructed parse tree, then it will be given towards the intermediate code generator. Now the 3 address code will be generated, that is x is equal to a plus b into 50. For this statement the 3 address code will be generated. So first t1 will be considered. So in the t1 the b into 50 will be stored, and t2 this will become the this will t1 plus a will become the t2, and the solution whatever available in the t2 will be directly stored in the x is equal to t2. So like this the 3 address code will be generated. For this address code, if any code optimization is necessary, then it is going to be doing. So you can see here in the code optimization, in the 3 address code generated for x is equal to a plus b into 50, we have taken t1 is equal to b into 50, So for this, here we have taken the, this will be considered as a T1 and directly T2 is equal to A plus T1 we have taken. So for this, there is unnecessary of converting again T2 in the place of T2, directly we can take S and in the X we can store the A plus T1. So unnecessarily we have written the extra statement here, so that by optimizing it, we can reduce 3 statements into the 2 statements here for this given expression. So like that, if any unnecessary code we have written, that can be optimized by the code optimizer. Finally, these 2 statements has to be converted into the target code generation, that is the machine level language. So first, in the first step, what it is going to be done, it is going to be done in multiplication, so that we can write the multiplication. Next it is going to be adding, so it is adding and it is storing into the some variable, so then it is going to be storing. So from this, it can be easily compiled and we have completed the compilation. So this is about the different phases of the compiler design. So once a program has to be compiled, it has to be gone through all these 6 different phases to complete its compilation. In between, if any error has been identified with the any phase, immediately it will be reported towards the error handler. By that, the user has to rectify the error, and if it is corrected and if it is again recompiled, then again the source program or the source code given by the user has to be gone through all these phases to complete its successful compilation. Thank you.